Modern enterprise infrastructure generates a massive, overwhelming torrent of abstract digital data that currently flows into a narrow, constricting funnel of human analysis. This creates a control vacuum. Despite significant investment in observability tools, these dashboards are primarily used to report system failures after the damage is already done. The incumbent pipeline follows a rigid, linear path. Raw signals are processed into alerts, alerts are converted into IT tickets, and those tickets wait in a triage queue. For high-speed AI clusters and cyber-physical systems, human triage is a fatal bottleneck. The time required for a person to interpret an alert and authorize a response exceeds the window for effective containment. Software value is shifting away from retrospective evidence. The new requirement is deterministic control, the ability to act before a signal becomes an incident. Tensor Networks designed the PTCP suite as a mathematical architecture specifically to execute this transition. PTCP operates as a higher-order control plane, providing topology-aware command across domains that were previously managed through isolated dashboards. This animated diagram illustrates the transition. We move from a linear workflow of signals, alerts, and tickets into a continuous, automated closed loop that allows the system to sense, predict, and stage control autonomously. By prioritizing automated action over manual analysis, PTCP changes the criteria for enterprise software, moving the focus from historical reporting to real-time operational outcomes. This control loop begins at the foundation, AI compute clusters. Currently, these environments are defined by pervasive GPU bottlenecks. Traditional MLOps schedulers view GPU utilization as a compute placement problem. They fail to address the underlying data path limitations that leave expensive hardware idle. Traditional network paths often starve GPU grids, shown by these red GPU wait blocks representing data stuck in transit. PTCP AI Factory introduces geodesic routing, mapping data path geometry. Watch the paths reroute, instantly converting red idle blocks into active green compute. This optimization results in measurable gains, a significant reduction in tail latency, and an increase in tokens per second per watt across the cluster. For the enterprise, these technical gains translate to capital expenditure deferral. By recovering idle capacity, organizations can delay the purchase of additional hardware. AI Factory converts network visibility into usable compute cycles, optimizing the infrastructure layer beneath existing schedulers. The exact same deterministic logic extends to physical operations, including drone defense, manufacturing, and industrial emergency response systems. Traditional video management systems share a critical flaw. They assign the same network priority to all physical sensor data, regardless of its operational importance. In a crisis, saturated network pipes flood with blue bulk video, blocking critical red command packets. PTCP-SARAHAI introduces a deterministic fast path. The pipe logically splits, prioritizing the red metadata packet so critical commands bypass the delayed bulk video. The system prioritizes the optic nerve, the metadata required for a decision, rather than just the volume of pixels that document the event. SARAHAI ensures that bulk data flows cannot starve safety-critical decisions, providing a level of reliability that standard physical security software cannot match.
In the cybersecurity domain, PTCP addresses the limitations found in existing SIEM, XDR, and NDR tools. Most security tools are reactive. They must wait to correlate events, inspect payloads, or match signatures before they can identify an attack. PTCP zero-day operates differently on this node graph. Data payloads remain opaque, but the system detects topology deformation, abnormally warping connections. This instantly triggers quarantine, forming a secure perimeter around the warped section before payload classification occurs. Zero-day shifts the defense posture from waiting on payload analysis to enforcing structural containment, identifying attacks by their movement rather than their content. Technical automation is only viable for a board or a CISO if it is paired with accountable human-authorized governance. Traditional compliance software often relies on manual evidence collection and retrospective reports that lack a direct connection to live technical state. ACISO functions as the governance layer. AI Factory, SARAHAI, and Zero-Day feed their control actions into a unified digital twin interface. This living risk model instantly generates a cryptographically signed evidence pack, creating a verifiable record of every decision.
To address concerns regarding autonomous systems, ACISO stages remediations for human-in-the-loop authorization, ensuring that major actions are approved before execution. This provides regulators, insurers, and legal teams with a signed chain of evidence for every automated response, reducing the burden of manual audit. ACISO allows security leadership to move beyond reporting past incidents to demonstrating governed, active control over the infrastructure. The commercial strategy centers on how PTCP interacts with the existing enterprise software ecosystem. In practice, large organizations rarely replace their entire software stack at once. PTCP is deployed as a control overlay. Categories like MLOps, SIEM, and VMS migrate from central authorities to subordinate data feeds. This facilitates a wedge sequence: land with a targeted use case, measure KPIs, license the module, and expand. A common entry point is a 90-day pilot focused on a single metric, such as recovering GPU capacity by reducing data path wait times. PTCP does not require the removal of existing tools. Instead, it turns them into inputs, securing the decision authority that defines high-value enterprise software. The competitive moat for Tensor Networks is the integration of mathematical topology with cross-domain control execution. Single-domain vendors lack the scope to match this combined value. The PTCP defense is a set of capabilities that are technically and operationally interdependent. Because the suite is modular, it is highly licensable. ISVs can integrate specific components to add deterministic control. To overcome procurement friction, Tensor Networks uses bounded A/B tests. These tests provide the specific performance data required for a technical and financial justification. For investors and architects, the value of simple data visibility is depreciating. High-density infrastructure now requires the ability to act on that data in real time to maintain efficiency. The ultimate asset is deterministic governed control. By owning the execution layer, PTCP provides a unified framework for managing AI, cyber, and physical operations as a single optimized system.